Yesterday we looked at this picture, all right? And in this picture, let me get rid of that for a second. We talked about the fact that the weight, if I put an object on an inclined plane, the weight of that object points straight down towards the center of the Earth. Okay, and then we talked about the fact that we could we could kind of manipulate our regular XY axis, and we could turn the XY axis so that the X axis goes along, the surface of the plane. We could kind of pretend that, and if we do it that way, then we could split the weight into an X and a Y component, right? Split it into an X and a Y component. And this X component is going to be the force that's going to make it pull down the ramp. And this Y component, that's going to be the force that's pushing it into the surface, or the normal force. Okay? So this force, this component, and these aren't forces by themselves, they're a component of the weight. So this force we called the parallel force. All right. Now this is not F11. It's not supposed to be F11. It's supposed to look more like this. That's the symbol you guys were taught in math class for parallel lines. All right. So the X component of the weight, if we call it the parallel force, we're going to call it the parallel force because it's parallel to the surface of the inclined plane. This component is the part of the weight of the box that's going to make it slide down the ramp. Okay? Now, the other component, that is the normal force, or the perpendicular force, because it's perpendicular to the surface of the inclined plane. So this is the force, or the component. I keep calling it a force. It's not a force by itself. This is the component of the force that's going to push the block into the surface, or into the ramp. This component of the weight, part of that will become friction. All right. So, and that all happens because of this. If we tilt the axis, we have an X and a Y. All right. Now, I want to do something. I want to move this. I'm going to move my parallel force down here. Okay. And the reason I'm going to do that, you guys, is because I want to show that, we have our same regular triangle, right? Okay. And then if I take this triangle, so I have the weight, I have the normal force, I have the parallel force. I'm going to group these. Okay. And if I do group them, oops, I didn't mean to resize them. Okay. So if I do group them and I turn it and I flip it, how do I have to flip that? Do I flip it horizontally? Oops. Flip. I think I want to flip it up and down. Nope. Oh, well, that might work. Okay. So these two triangles, if you look at them, especially if I had done this perfect, right? Do you see that the angles match? These are similar triangles, right? And so that angle matches. This angle is going to match this angle. They're exactly the same. So if I know the angle of the incline, I know that angle. We talked about this a little bit yesterday, but I know that some people were just a tiny bit confused. I don't think it's your fault. That's more likely my fault. Okay. So if we put this back the way that it was here, and I got to flip it again. I flip it left and right. Oh yeah, I did. Okay. So I'm going to put it back. Oops. I'm going to put it back to where it was. So this, remember, this is the weight, and it's pointing straight down into the center of the Earth. Then I have the normal force that's going perpendicular. I have the parallel force that's parallel to the surface, and that's going to be the component of the force that's going to make this slide down. Okay, so this parallel component, that's going to be equal then. If I take the angle of the incline, because that's what you'll be able to measure today in your lab. If I take the angle of the incline, right, that would end up being the opposite side. So we're going to make this mg times the sine of theta, where we're measuring theta, you guys, with the angle of the incline. So switch that up, all right? Now, this normal force, that's going to end up being the adjacent side, all right? And we don't really care about the normal force so much as we care about friction. So let's just write it here. If I want to find friction, that's mu times the normal force, right? So if I want to find friction, that's going to end up being mu, the coefficient of friction, times mg cosine theta. So this is going to be friction, and this is going to be the component of the force that's making it slide down the ramp. So if I were you guys, I would write that down. Okay, erase what you did yesterday, because like I said, I think I was confusing some people, and replace the equations that you have with these two. Where, remember, the angle is the angle of the incline. So for today's lab, this is what you'll be doing. You're going to take a ramp. So you're going to take some long board, or doesn't have to be necessarily long, but you're going to have some board, something flat that you can lift up, all right? Now you're going to put something onto that board, whether that be, I don't know, like a cereal box maybe turned on its side, or whether it's your phone, whatever it is, okay? And you're going to lift up one end of the ramp until this just starts sliding down. Not accelerating, but sliding down at exactly a constant speed. So it's barely going down the ramp, and it's going down at a constant speed. If that is true, right? There's two forces acting in the direction of motion. One would be the parallel force, which I could calculate with the weight of the object times the sine of the angle. The other one, opposing motion, would be the friction force. That I can calculate by taking mu times the weight times the cosine of the angle, all right? And if it's going at a constant velocity, right? Constant velocity means the acceleration is zero. That means that the net force is zero. Okay, that means that when I do the applied forces minus the opposing forces, they have to be the same. So this perpendicular force is going to have to be the same as friction in order for it to slide down at a constant rate. So for this lab, if you do it right, let me separate these. The perpendicular force will equal the force of friction. Okay? Now what I want you to do is I want you to put your material on the ramp. I want you to lift it up till it starts sliding at a constant velocity. Then you'll know this, parallel force and your friction force are going to be the same. Okay? You're going to have to get the weight of your object. Now that can be difficult for you guys, right? You may have to do some estimating. If you use a phone, you can look up the weight of your phone. If you use a box of something, I would suggest going in to your pantry, right? Finding in probably smaller boxes of food items that haven't been opened. They have weights right on the front of the box. Now they won't be totally accurate because there's a little extra weight of the packaging, but they'll be pretty close. They'll be good for estimates. So you would need to know this weight. And actually, you guys, if you do the math and you figure it out, there is a way to do it without the weight. Just letting you know. But I want you to slide these things down, and the goal is to calculate this coefficient of friction. I want you to try to get the coefficient of friction. All right?
Mr. D.
Yeah.
So it doesn't seem like you really need the normal force then for this equation.
Well, so here's where you need the normal force. This right here, the weight times the cosine of the angle, that is the normal force, right? That's this one right here. Because the force of friction is
Okay,
mu
yeah.
times the normal force. Does that make sense?
Yeah, because the F11 is the friction force.
Right, right. No. Well, they have to be the same. It's not F11, it's F parallel.
F parallel.
Right. So if you guys for this lab here, I'm actually gonna. I might as well just show you. I was gonna have you figure it out on your own, but you're all smart enough. You would have figured it out. So if I clone this page, this is what I want to show you. Right. If all right. So I know that the parallel force is going to be. I know that the parallel force is going to equal the friction force, right? So then that would be mg sine theta equals mu mg cosine theta, right? Because friction is mu times the normal force. Do you see a term that is going to disappear here? Someone shout it out.
mg.
Yeah, mg. The weight, it doesn't actually matter, you guys, for this lab. Okay. So if I'm solving for mu ends up being the cosine of the angle. Oh, I'm sorry. It ends up being the sine of the angle. Ah. It ends up being the sine of the angle divided by the cosine, where the angle is going to be the height or the angle for the ramp, the angle of the incline. Now, to get that angle, you guys, you can use your phones.